So with all of that put aside, I'd like to introduce you to Al. Al is our, can I say expert?
Sure.
Al knows a lot about nuclear energy. I don't think other than Oppenheimer, there is anyone who's truly an expert, eh?
Yeah, probably. Yeah.
So I'll take it over to you.
Sure, thank you. Well, good evening, everyone, and thanks for joining us tonight. I can do something, well, two things. I'll let you know, I'm carrying around some notes because there are some things in here I had to refresh myself on. I want to make sure I share good information with you. Okay, that's my purpose here, is to share good information with you. And talk about, call here, nuclear power and SMRs. SMRs, of course, means small modular reactors. I call this a primer. A primer is just meant to be an information session, and it comes from, and I'm proposing to do this for people who I think may want to end up supporting nuclear power. So I will say up front, I'm a supporter of nuclear power. I've been involved in the mining industry for more than 30 years in a variety of capacity, and more than half of that, I've been working with mining companies who have given me experience in nuclear, primarily Cameco Corporation, world's, I think, presently now second largest uranium producer. But I was with Cameco when they got into nuclear power directly by investing in Bruce Power in Ontario. But Cameco plays a really big role in the whole nuclear fuel cycle, and I've been lucky in my career, both through Cameco and where Cameco sent me to work to gain experience with nuclear. I've also been involved on the uranium front, working with communities to help address concerns that may exist with respect to environmental matters or health and safety matters, regulatory concerns, all those things. So I'm not a nuclear engineer, so this is not going to be a technical talk about the physical nature of a nuclear power plant, any of those things. I'm going to talk about all the other things, like safety and environment and radiation and all the things that people maybe wonder about when it comes to things in the nuclear industry. And I want to thank you for coming tonight. I'm going to point him out not just because he's my brother, but my brother came with me. He's in the aviation industry. He and I, in our careers, often talked that aviation and nuclear share some things in common. We share a safety culture. We share a real strong desire in the industry to have no accidents. And we try and design that into the technology we use and the practices we use and all those things, because both sectors are really dedicated to safety. So I want to say that up front. The other thing I want to say is I'm very happy to be here because we have family roots here. Both my grandfathers were coal miners way, way back when they first came over from, quote, the old countries. One of my grandfathers on our side, my grandfather Shpyth, left coal mining and opened Tony's store, one of two general stores in Beanfate, Saskatchewan, a long, long time ago, which he ran until old age prevented him from doing more of that. Our other grandfather, our grandpa Hitchin, he was a coal miner his whole life down here in the area. The last machine he worked on was on the dragline that walked. I don't know if anyone here has ever seen the dragline that walked. So that was the last bit of coal mining equipment our one grandfather worked on. So we are Shep, last name, modified Polish. Hitchin, we've got Prisniks, Antnuks, several family names, primarily in Beanfate area, and I hate to say, now primarily in the Beanfate Cemetery. But yeah, we have family roots here that go back a long time. So that's the other reason I'm very happy to come down here and talk about it. And I'm the only one in the family not born here, but I have memories of coming here for summers with grandparents and swimming in the coal pits, tobogganing down the hills in Roch Percy when I was old enough, going across the line to Portal. So if you grew up in SVN area, you probably shared some of those experiences as you were growing up. And I am very happy to have this opportunity to share with you my thoughts, my experience on nuclear and small modular reactors. I do hope you enjoy the event. I do hope I speak to the information you are seeking. And if I don't, I'm quite happy to take questions and work, to try and give you the best information I can. And as noted, this can be an emotional issue for people. Nuclear power has had its experience of controversy over the years. It has accidents. It has had some accidents. I will talk about safety of the sector overall. And we're considering the option of nuclear in this province in a time of change. Right? There's great change and debate going on with regards to energy. So I know that's the larger context, and I know that context has an impact here in this region because of its potential impact on its impact that it's having on the coal industry and the future of coal. So I know that's going on, and I respect the challenge of it. One of the first mining company I worked with was a German company. I happened to work with them at the time when the Germans announced they were going to shut down all their nuclear power plants and rely on natural gas from Russia. I can tell you it shocked German industry when that decision was made. Absolutely shocked the industry. And now you may know Germany's questioning whether or not that was in fact the right thing to do all those many years ago. And the last year after the Russians invaded Ukraine we're actively looking to see could they salvage what was left of the nuclear power industry there, because one of the great things about energy that we've grown up with is it's provided the energy we need for our economies. It's provided the energy we need to heat our homes. It's provided us with energy security and all these things that I think that's still important to know. That's things that we value out of energy. Now, energy can also come with environmental impacts. It can also come with safety impacts. So that's why I'll try and build some of that in here for you. So I think small modular reactors as a technology that can play a role in Saskatchewan's future. I'm very interested in SaskPower's efforts, and I'm very interested in, I think what you're wanting to learn about them, as this community is one of two potential locations for small modular reactors in this province. So does that sound reasonable? There's other things you want me to speak to? Let me know. So the topics, and everyone see okay? Okay, so I will talk a bit about small modular reactors, what they are. I'm sure you've heard about this from SaskPower. I'll just give you sort of a general perspective. Talk about the approval process, where I've spent a lot of my professional career in is getting things approved. I'll talk about some of the issues and concerns I know have been raised about nuclear power for as long as I've been in the industry and involved, which is 30 years. And at the end, I like to talk about some of the actions that if you're interested in supporting the nuclear option, I think some of the things you may want to consider taking on. And again, I'm very open to questions and very happy to discuss any of the topics, any of the questions you think you may have. So up first, about SMRs. So SMRs, so anyone here actually with, not with SaskPower, but involved in power generation here, history of power generation? So SMRs in our ways are like the coal plants that have been down here for a long time. They're also like natural gas plants in that they're thermoelectric sources of electricity. Heat is generated, creates steam, steam turns turbines, and away we go, we get electricity. SMRs, they can be baseload like coal. They can also load follow like natural gas. And that's part of the attract of the SMRs. The large nuclear power plants, the ones that are in operation today, are predominantly baseload plants. That's where they run best. SMRs, again, are different because of their size and other features. They can act both like a coal plant, both like a natural gas plant. What differs, of course, is unlike the fossil plants, the fuel that goes in to generate the steam is not burned. It's not combusted, so there aren't combustion gases that come out the other end. The fuel goes in as a solid, and when this fuel is used up, when it's used fuel, it comes out as a solid. And that's also one of the, I think, key features of nuclear from many people's perspective. So quickly, of course, small means they're less than 300 megawatt electric units. Shand, if I remember correctly, is 276 megawatt. So it's quite comparable to Shand. Ideally, small modular reactors are going to be modular. They're going to be built in manufacturing centers, in manufacturing plants, multiples at the time, and you're going to get the benefits of manufacturing. And largely, if not as an entirety being shipped to site, big components are going to be shipped to site, already built in a factory setting. And modular is really key to the future of SMRs to help bring their cost down. large nuclear power plants, and the challenge is they are 100%, basically 100% constructed at site. And unfortunately, in the last decade or so, the new big plants that have been built suffered really significant cost overrun issues. So hopefully modular is going to help on the cost front. And the reactors, which again fundamentally means they're fueled by uranium rather than coal or natural gas, and they undergo a process called fission. So everyone, is there other presentations talk about fission? I'm just trying to see how much I should go into. So fission is a nuclear process. The nuclear industry, like every industry, has its own unique bits of language. Hopefully, anytime I use a phrase I think you've not heard of, I'm going to try and explain it a little bit. So there's what they call an incident neutron. It's something that starts. It collides with, called the fissile nucleus. That's uranium. Uranium's a very large, heavy atom. In that collision, it splits the nucleus in two. When it gets split into two, it releases a great deal of energy. And I'll talk very soon about how much energy it releases. It also releases 2 or 3 more neutrons. Those neutrons then collide with other atoms, and you get a chain reaction. You get what's going on that's called fission. For those who are a little bit more into the science, I've met John, so I know there's a physicist in the room, so he has me beat on that. This is how it looks like in the type of reactor that's proposed for use in Saskatchewan. You got this incident neutron hitting uranium-235. Uranium-235 is what's called fissile. It can undergo this reaction. It becomes unstable. It splits into 2, and out come 3 neutrons the other end, and the chain reaction continues. So that's how fission works. Really key is it's uranium-235, and I'll talk about that in a moment. And it's amazing, how much energy. 1 gram of uranium-235. I can't even describe you how small 1 gram uranium-235 is. It's very small. Produces 1 megawatt day of energy. So for the power coal person, that's a great deal of energy from it's like a grain. It's an incredible amount of energy is contained within uranium. Which takes me to how much. Here are some examples. These are ones that have been pretty standard over the years. So you've got 1 uranium fuel pellet, which is about the size of your fingertip. Produces as much energy as 17,000 cubic feet of natural gas, 149 gallons of oil, or 1 ton of coal. And that's not lignite coal. That's the high-grade coal that you get out of the Wyoming mines, for example. So there's a great deal of energy in uranium. And to turn into maybe a bit more for us, 1 kilogram has 2 to 3 million times the energy equivalent of oil or coal. 2 or 3 million times as much energy. Yes?
I was just curious, so you mentioned fuel pellets.
Yeah.
Does the SMRs that are kind of in question here utilize a small pellet rather than a rod, so it limits the actual fissile runaway?
I have a graphic in just a moment. Pellets get assembled into rods. Rods get assembled into bundles. Bundles go into the reactor. Yeah, that's a very fair question. So it's called energy density. You may hear about it, energy equivalency. It's just really amazing how much energy there is in nuclear. When I worked for Cameco back in, I'll just pick the year 2010. This was one of the last years, McArthur River, a mine in Northern Saskatchewan, once the world's largest, richest uranium mine. 1 mine, total area of McArthur River, 1 square kilometer. The uranium from that 1 mine could fuel 2% of world electricity. Mines from Saskatchewan fueled 20% of all US production for many years. So the amount of energy that comes out of uranium is very significant. Last year in the US, nuclear power plants produced 772 billion kilowatt hours of electricity. enough electricity for 72 million homes, and it's the largest source of clean energy in the US, larger than wind, twice as large as wind, 5 times as large as solar in the US, from 32 reactors in the US. So again, great deal of energy comes out of it, out of nuclear power. And that's one reason. The amount of electricity a nuclear power plant can generate is one reason why they're under consideration. And there's some other reasons SMRs are being attractive. These are the new types of nuclear power plants. They are, again, small, modular. So they have lower initial capital investment, very large nuclear power plants, which are 1,000 megawatt and larger, some 1,600 megawatt, have very high capital investments up front. But these have lower capital investments because of the energy density. They have really high capacity factors. The one that's proposed here in Saskatchewan is proposed to have a 95% capacity factor. That means it's generating electricity 95% of its time, which is quite high. They're greater scalability due to them being modular. So they're not only being looked at by utilities like SaskPower for electricity, they're being looked at by industry. Because you could have 1, 2, 4, 6 of them. They can do different things with them to meet your needs. They could produce electricity, they could produce heat, they could produce combined heat power. They're really flexible, these SMRs that are coming out. They also have siting flexibility, given their size. They can go places that you can't put traditional large reactors. They have enhanced security, safety and security compared to earlier designs. Many of them are called Generation 4 reactors. Generation 1 being the very first reactors built, back in the 50s and 60s. Then Generation 2 sort of came online in the 70s and 80s, and Generation 3 came online in the 90s. And now we're on to Generation 4. A lot of the SMRs are Generation 4 reactors, and they've got, again, these enhanced safety and security built into them. And the other thing about them, so related to their siting flexibility, given their size, they can readily fit into infrastructure of fossil fuel plants that are being closed. Again, the SMR, BWRX, is about 300 megawatts, about the size of Shan. They can fit in well into grids and infrastructure that already exists for coal or natural gas plants. So that's one reason. The other reasons the XXRs or the SMRs are being attractive. Now, I just want to say very little bit about the GE Hitachi BWRX 300, which is the SMR that's being considered for Saskatchewan. Or has everyone heard enough about this? Or I only have one slide on it, so I'll try and be. It's fundamentally, it's a boiling water reactor. So again, it's also very similar to the coal plants here. They heat, they boil water, create steam, generate electricity. So they're boiling water reactors. It's one of 2 really dominant reactor types currently exist in the world. The other is a pressurized water reactor. This is a boiling water reactor. So again, uses uranium to boil water, to make steam, turns turbines, make electricity. So outside of the nuclear plant, everything else is like already at Shannon boundary in the lake. It's from the generator on, it's things we're quite familiar with. It uses what's called low enriched uranium fuel pellets, which again, get assembled into rods, get assembled into bundles. I'll talk about enrichment in just a moment here. Each fuel pellet, basically each then fuel rod assembly, can provide up to 5 years of fuel for heat for power generation. And when they're used, they get pulled out and they get replaced. And the reactor keeps going. And again, the uranium goes in as a solid, it comes out as a solid, it's not burned. Sometimes you will hear people in the industry talk about uranium being burned. It's not burned in the traditional sense that we're used to with coal, but because it's not combusted, there are no combustion byproducts like SOx and NOx, particle ash, any of those things, or greenhouse gas emissions. So you're probably aware this particular reactor type has been picked first by Ontario Power Generation. They were going to build 1 reactor as a demonstration. They've recently announced they're actually going to build 4. And according to the SMR plan for Canada, SaskPower is also considering 4. So uranium enrichment. I said these require enriched fuel. The uranium we mine in Saskatchewan, I'll call it natural uranium, it's less than 1%, 0.711% uranium-235. That's the uranium, the fissile uranium that can undergo a chain reaction. The vast majority of it is uranium-238, an isotope, a different isotope of uranium. Okay. Uranium-238 is not fissile. It cannot undergo a chain reaction. It cannot contribute energy to that process. So low enriched uranium fuel, as we call it in the industry, has greater than the natural amount of 0.711%, but less than 20%. So through technology, you basically are trying to increase the ratio or the relationship in the amount of uranium-235 to uranium-238. All the late water reactors in the world, and they're called that way, including the boiling water reactors that GE makes, typically use fuel enriched to about 3 to 5% uranium-235. The BWRX will use that enrichment level. CANDU reactors, if anyone's heard of the CANDU reactors, the Canadian design ones that are running in Ontario and in New Brunswick and may reopen in Quebec. They use natural uranium. They can actually take, quote, the uranium we mine in Saskatchewan, they get a process turned into fuel, and it can go into the reactor as is to generate electricity. It's one of the few reactors that can use natural uranium. And at the other end, not for fuel purposes, are, quote, what's called highly enriched uranium, which is greater than 20% enrichment levels. It's used in the nuclear power plants that power ships. There's more than 400 nuclear-powered ships sailing the seas. They use it for propulsion. It's in some research reactors. And honestly, it's in nuclear weapons. Nuclear weapons are enriched to greater than 90%, like significant enrichment effort required for the weapon cycle. But the commercial system, it's 3 to 5%, and that's what the reactor that we're going to have here will run. Yeah. Please go ahead. Yeah.
Where, for example, would it be enriched?
Sure. Great question. Takes me to my slide. Yeah, the nuclear fuel cycle. So these are all the steps involved in the nuclear fuel cycle, from the mining of it all the way up to its final disposal. And we're one of the biggest uranium miners in the world. We're not the largest. Kazakhstan is. We mine it, comes out, we call it ore in the mining world. It gets milled. The ore gets turned into a concentrate as it's a powder. It has a chemical form, U3. I'm only mentioning the chemical form because it sort of changes all the time. Then it goes on to a refining step. All the trace elements, impurities are taken out of it. So you really get a really pure uranium concentrate which is UO3. Goes into a conversion step for light water reactors. Goes into enrichment. Conversion turns it into something called UF6. UF6 gets enriched for fuel, gets turned into UO2. UO2 gets sintered, gets baked. It's like a ceramic process. And under high pressure gets turned into pellets. Pellets get assembled into bundles. Bundles get assembled into assemblies. They go into the power plants, generate electricity. When the fuel has been used, it comes out, gets stored initially in water for several years, and it gets put into steel and concrete canisters, and ultimately it'll be disposed of in deep geological disposal. So all these steps, but enrichment happen in Canada today. This happens in the US, happens in Europe, also happens in Russia. I won't talk about, again, the Russians, their invasion of Ukraine has had an impact on their ability in the market. And we're also not yet at the stage of disposal in Canada, but we have an organization called the Nuclear Waste Management Organization. One of the great things I think about the industry is all the way through, there's a responsibility for the material. Cameco Mines and Mills has money set aside all the time to close down the mine, decommission it, and clean it up. Anyone who does these steps has money set aside to take care of site closure, cleaning up. Yeah.
And those conversion refining, is that done kind of at mine site or in Saskatchewan, or is it sent away for that?
It could have been done here. The refining happens in Blind River, Ontario. The Blind River refinery was originally called the Warman Refinery. If you've been around long enough like me, it was originally proposed to be built in Warman, Saskatchewan. It got turned down, and the people in Blind River went, we've had uranium mine in Northern Ontario for a long time. We're really comfortable with it. We'll take the 200 jobs. And they took the 200 jobs, and it's there for ever. The conversion plant in Canada, one of 4 in the world, it's in Port Hope, Ontario. It also is a really interesting story. I know way too much about this stuff. It was the second radium refinery in the world, opened in 1933. You want to know this story? Way back, after uranium was discovered by the Curies, Madame Curie, you may have heard that name, and they figured out it could be used for medical purposes, was where do you get it? The only place in the world at the time was in the Congo, the Belgian Congo. Way back, 1920s, your radium was like $30,000 an ounce. And then we discovered uranium in the Northwest Territories in Canada. And we started to mine it, and it needed to go through this process somewhere. And the person, I know why he picked Port Hope, Ontario, because it could be flown and or barged out of the Northwest Territories into the Athabasca River system, into Edmonton, onto the train to Ontario, to an old sugar refinery that he basically got for $1. It was closed down in the 1930s, Depression. So he got a refinery plant on a rail line system and on the Great Lakes for shipping. And he opened up the first radium refinery, second radium refinery in the world, and the price of radium collapsed to like some very low amount because a competitor opened up to the Congo. So yeah, it's a real long history there. But yeah, there's only a very small number of those in the world. Same thing, there's not that many enrichment facilities in the world. And that's because, well, most of the nuclear fuel cycle is associated with power generation. It was born out of the nuclear weapon program in the United States. So enrichment is a controlled technology. We take great care, and there's lots of treaties and other standards around enrichment in the world because it can be used for great good, generate electricity, but it can also be used again in the weapons process. Now, none of what we mine in Canada enters that cycle. Everything we do in Canada is tied completely just to electricity generation. Yeah.
So with the involvement of nuclear energy,
Yeah.
Is there going to be an opportunity or need for additional facilities for enrichment?
There is going to be a need for some. I'm going to generally say yes. I'm going to say generally because a lot of the new reactor types also want to use new fuel types. And those new fuel types are also proposing to enrich above the normal or regular 3 to 5%. Cameco has been investigating, and I'm not speaking for Cameco, I just know from history, they've been investigating a new type of enrichment technology that they're considering. So I can't speak for them, but I know they have that potentially. And of course, because it's Cameco, because it's a Canadian company, all that, it would be just, if it gets built ever, it would plug into the commercial fuel cycle, it would not be part of the weapon cycle. So, but depending on, how the market goes, if all the countries who are today talking about nuclear power proceed, and if all the potential SMR plans proceed, there will be an increase in demand, I think, probably throughout the whole process here.
Does the treaty have to get modified at that enrichment process before they can build more? Is that how that's?
There'll have to be a going by memory test. And because Cameco is not a government-owned entity, again, it's outside of that cycle. But historically, when Cameco has been looking at where it could be built, they have been looking at the United States historically, because the United States, because of its history, already has provisions for managing enrichment, which, because we've never been involved in it. The CANDU reactors don't require enrichment, so we have no history with it here. And then, so just to give you some, interesting context for what all happens here. So again, you go through all this process, and if you go through the enrichment cycle, if you had a 1,000 megawatt reactor, which again, 3 times the size of what's being considered here, about 27 tons of fuel would go into that plant every year. So it's a big plant, small amount of fuel going in. Within the 27 tons, just, there's about 18 million fuel pellets. Because fuel pellets are really small, right? So they get assembled, yes. Oh, sorry, I didn't fully hear, sorry.
Where
Yeah.
in the US is it enriched? On what state?
I'm afraid, going by memory, I don't remember where the US enrichment plant is.
I tried to figure out
Yeah.
the trajectory, the journey that this substance made.
Yeah.
Until it ends up in the power plant.
Right.
So how many kilometers does this substance go?
Yeah, it's a very interesting question. It can be very far. So again, so let's say we do, right? We mine and mill here in Saskatchewan. It will get for our product, it gets shipped to Blind River, Ontario by truck, typically, which is in Northern Ontario and the shores of Lake Huron. It goes from there to the Port Hope conversion plant, which is in Southern Ontario and the shores of Lake Ontario. And from there, it can go to the US plant or a French plant or a UK plant. And then the fuel fabrication happens in several other places. There's several companies involved in fuel fabrication, again, going by memory. And then, the fuel is shipped to the reactors. Again, there's more than 400 reactors in 32 countries around the world. So this can travel a good distance.
Why can't we figure out maybe before we build a plant that we can do everything local from the beginning until the end, the stockage of the thing. It's not ready yet, right? When the fuel once is used to put it into the ground, we don't know where to put it yet. Is that right?
So I think, 2 questions. One is, how come this can't all happen, quote, local? And the other is being, at the end, we don't know where it's going, right? Those are the 2. So part of it is how the industry has grown up. Mining, milling happens in many countries around the world. Again, going by my memory from my trips to the Blind River refinery, over time, they've taken uranium concentrates from more than 60 different mines around the world. But again, this plant already exists. It's one of only a very small number of plants. This plant already exists. It's one of only a very small number of plants. So, because they exist, I can't, until the demand is there to possibly justify building new ones, we're going to continue to use the plants we have. There is opportunity. People are wondering again, where should new enrichment plants be built? Where should new fuel fabrication plants be built? Certainly, obviously, where should new power plants be built? Right now, storage happens right beside the power generation plants, is where storage is happening right now. Disposal, I'll just briefly say, in the Canadian process, Canada basically opened up the opportunity to host a deep geological repository to many different communities across the country, provided they were connected to the Canadian Shield. So the view in Canada is the best place for a deep geological disposal is in the Canadian Shield, deep, solid granitic rock. Other countries have looked at salt domes and other geological formations. We've picked the Shield. There are presently 2 communities being considered for the final location. They're both in Ontario, in part because the vast majority of the used fuel is in Ontario, because that's where the vast majority of the nuclear power plants are today. And under the Canadian law, all used fuel from all power plants will end up at this one repository. If I, again, remember correctly, the NWMO should be making a decision next year on which of those 2 communities. So they're wanting to find what's called a host community. Sweden has done this. I visited the Sweden facility when it was under construction. The Finns have done this. Several other countries. Every country pretty much that has power generation is looking to site within their own country a deep geological disposal facility of some sort.
In terms of the spent rods themselves,
yeah.
Are they? My understanding is that they're hot, right? They're extremely hot, and they're too hot to be able to be used anymore in a traditional reactor. Is that assumption correct, or are they more cold and there's no reactability within them? And is there a potential for spent rods to be reused as a continual source of energy?
Great questions. Again, I'll give you my non-engineering answer is yes. So, to all that. When they come out of, certainly out of the existing reactors today, when they come out, they are both hot from a temperature perspective. They're also hot from a radiological perspective. And they get put into, for several years, into very deep storage water pools. I will talk in a moment about half-life. So one of the things, when you split the uranium-235 into those smaller nuclei, those nuclei are more radioactive, but they're all contained within the fuel rods. So it takes some time to cool them off. So it's after several years, it depends on the fuel type, 7 to 10 years, let's say on average, and then they're cool enough, so to speak, both from a heat and a radiological perspective. They can be put into storage canisters, and the storage canisters have all been designed, the Canadian one's been designed for use for 50 years. They exist at all nuclear power plants. You can walk up to a storage canister and put your hand on it, because of the shielding and other things, but the radioactivity is greatly marked off. Over time, as the radioactivity level continues to fall, the heat continues to fall, you can reuse those fuel. You can, quote, reprocess them. 95% of the energy that goes into a CANDU reactor fuel bundle still comes out the other end. And I was told once that with a CANDU fuel type, you probably could recycle it 7 times. We don't recycle today in Canada. The recycling effort to create what they call mixed oxide fuel these are very large, very expensive, multi-billion-dollar plants. Just looking at Gordon, tell me if I'm talking too much, okay? So
No, I'm monitoring.
Great. Yeah. So recycling, reusing a fuel is happening in France. It's happening in Japan. It is certainly one of the options looking forward. And one of the other interesting things with SMRs is they're also designing these new reactor types that are designed to take used fuel and reuse it. So the New Brunswick Power, another utility who's part of the 4-province deal in Canada, is looking at a new reactor type called an ARC. And the ARC is designed to take used fuel and basically reuse it without having to go through that whole, quote, big mixed oxide process. So
we have another question.
Yeah.
And let's just keep doing this. I think.
Okay. Yeah.
It's good. Rebecca.
Mine was just to add to the disposal question that she had.
Yeah.
The NWMO, I think it's a camper trailer. They basically cleaned out this giant trailer and they've created this display to discuss what happens with the disposal. And it's actually, Councillor Groban and I went through it when we were in Ontario in the spring. But they're actually starting to do a virtual tour as well. I think if you want to get a hold of them, they'll kind of tour you through this trailer, and they're kind of trying to get it a little more technical. But it goes through the whole site selection of the disposal and the process of it, and it's super interesting. If you ever get a chance or get an hour kind of to research this. It's really cool. And Saskatchewan is actually, they had 3 locations in Saskatchewan out of the 22 that were
Yep.
presented, I think, and they kind of got kiboshed. But yeah, if anybody is interested, they do have a really cool presentation for disposal.
Yeah, I agree. Having seen the one in Sweden, it's really advanced technology, engineering, design, effort. It is. Yeah, I would agree. I'd say it's cool too, but yeah.
Can you give us a website later on then?
Yeah, for sure. Yeah.
Yeah.
That'd be great. Thank you.
Yeah. So that's the fuel cycle, and yeah, happy to talk about it a bit more. This was a question of, again, how does this work? So again, a fuel pellet gets created. It is size of a finger. It's about 1/2 inch diameter. This is American drawing. Sorry, 1/2 inch. So gets into zircaloy, a particular metal assembly. They get created into fuel rods. A fuel rod's about, in this case, about 12 feet tall. Several fuel rods get put into a fuel assembly, and a fuel assembly goes into the reactor. When it's done, again, it comes out, gets stored, and then eventually the whole fuel assembly right now is getting put into these big storage containers, canisters. Yeah.
So if I'm understanding the way that drawing is showing, is that the pellets are just slid into a sleeve? Is that a correct interpretation?
It's a tube.
Yeah.
After they're slid in, the tube gets sealed on either end. I've seen the fuel assembly or the fuel manufacturing complex. There's actually 2 of them in Canada for the CANDU fuel system, and I saw one in, of all places, Russia many years ago, run by a German company. By chance, but yeah. So the pellets get in, everything gets sealed. There's actually some very specific design elements into the geometry of a fuel bundle, which helps to both encourage the chain reaction from happening, and also allows, if you want to turn the reactor off, so to speak, the geometry is designed to allow you to do that as well. Or in the case of the small reactors, to load follow, so you can change the level of activity that's going on in a reactor type. So yeah, I thought this is basically what, if a reactor gets built in Saskatchewan, what a fuel assembly will, at the end of the day, look like. So as I said, if one gets built, so again, this sort of takes me hopefully into an approval process. The approval process we're going to follow in Saskatchewan differs from the ones that's happening in Ontario to some degree, and the one that's happening in New Brunswick to some degree, because in those provinces, they're looking at these new SMRs on already licensed, approved nuclear sites. We don't have that here. So our process is going to be slightly more involved. At the federal level, we have something called the Canadian Nuclear Safety Commission. It's existed for a very long time. Its mission is to protect the health and safety of the public and the environment. They're responsible for licensing the design. They do a significant amount of work looking at the design. Is it engineered well? Is it designed well? Will it, again, provide fundamentally for protection of people and safety of the environment and the design? They are responsible for the licensing the full fuel cycle. So they license uranium mining and milling, the refinery, the conversion, all those steps they're involved in. So there's regulatory oversight, several hundred people deep involved in regulating the industry. And so again, that involves the site preparation, construction, operation, decommission at the end. There also will be responsible for licensing spent fuel management and disposal. When the NWO picks a spot, they're involved. And this is very common in the US. They have the US Nuclear Regulatory Commission. All countries are using nuclear power have regulatory commissions, and they collaborate. They follow international standards. It's all part of that culture of safety. The regulators cooperate on things as well. Then we also have, from the environmental perspective, now in Canada, something called the Impact Assessment Agency. And they will do what's called an impact assessment. They'll look at where it's being located, what are the environmental factors, are there potential community impacts, quite a variety of things. And they'll have to make a determine, are the impacts, quote, acceptable, which is at times can be an interesting question, I'll tell you from my life. So the technology SaskPower has chosen is subject to an impact assessment under the Federal Impact Assessment Act. Okay, so in addition to being reviewed by the Nuclear Safety Commission, it's going to be reviewed by this Impact Assessment Agency. And that's because even though it's a small modular reactor, it's bigger than a threshold limit, which is 200 megawatt. And it's also not located within the boundaries of an already approved site. So remember, they have to approve the site. We don't have an approved site here yet. So they have to look at that as well.
Question.
Yeah.
Does that Impact Assessment Act hinge on both of those conditions, the thermal capacity condition and the Class 1A facility condition? Or if you're not meeting either one of those, you skip the impact assessment?
So if you're smaller than 200 megawatts, you won't trigger the federal impact assessment, but it's a nuclear facility of any kind in Canada is what's called a Class 1A facility. So that's not a threshold issue. It's reactors.
Right. So if you were building a new plant
at
a brand new site that was less than 200 megawatts, you would not trigger the Impact Assessment Act. Is that right?
There's an and here. The ones that are under consideration today are all greater than 200 megawatt and at a site. It's environmental law is fundamentally about administrative law, so someone will really read, is it an and or a may or the should or a must or but they're all going to get looked at. One of the I'm going to say hope, I think that's the right word for small modular reactors is, again, we want to have modulars, we want to have many of them built, and what we're also hoping is ultimately the application process, the approval process will look at, okay, so this is not the first of its kind, it's the 50th of its kind, right? And in already reviewing it 50 times, we have a really good idea that its design is solid, and we already have an idea of how it interacts with the environment. So as long as the site meets these conditions, that's what the industry hopes we get to from a regulatory perspective. But the regulators are independent. They do what's called a safety case. They will always look at what's the safety consideration in place, and they won't relax the requirements if they think there's a safety issue. And I have many years of experience. They will not relax the requirements if they think there's a safety issue. They're independent, that's their mandate, that's their charge. And I can tell you, they take it very seriously. Yeah.
So with that the small, like the micro nuclear reactor that's kind of being kicked around by Westinghouse, they might run into a pile of impact assessment issues with, even though it's able to be mowed, they'll likely run into a lot of regulatory issues despite its size.
Yeah, I've been trying to think through that a little bit. So he's asked about what's called an eVinci microreactor. It's proposed by Westinghouse. They've partnered with the Saskatchewan Research Council. People aren't always fully aware. We actually have had a very, very, very small microreactor operating on the University of Saskatchewan campus for many, 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 many years. So, and the SRC held that license. So the SRC has been a licensed nuclear operator, and Saskatchewan has had it was very small. Like it was literally the size of a 5-gallon pail. It was small, but, and we do have other, in addition to the uranium mines and mills, who's heard of the Canadian Light Source? It's a licensed nuclear facility, not far from my office in Saskatoon. Like, we have history here. So there it is. said there is a lot of consideration, still a lot of discussion internationally between the regulatory authorities of, okay, how really do we want to look at those micro reactors? Because even micro reactors are from small, less than 5 megawatt to 30 megawatt. Some of them are designed to be a battery. And that's really the best way to envision it. It's a battery that will run for 20 years. And it's smaller than a house. And you literally would just pick the battery up and take it away to the plant that manufactured it to probably remanufacture it and send it back out. But the 30 megawatt ones are slightly different. They're not quite batteries. They're so yeah, there could yet be some complexity for the micros as we work through that. And I just very recently in New Brunswick, they have filed their application for the environmental impact assessment process. I didn't get a chance to look to see if it's federal or federal and provincial. Because again, it's New Brunswick Power, already licensed nuclear operator on an already licensed site, but it's 100, I have to confirm again, it's 200 megawatt thermal or 200 megawatt electric, because the ARC, which is what New Brunswick Power looking at, is 100 megawatt thermal, no, 100 megawatt electric. So that's still being worked through a bit. And I was at a gathering the other day when someone asked about the timeline for this. The federal regulatory process is projected to take 7 to 9 years. It is very thorough. It is very substantive. Provincially, we also have a requirement for environmental assessment in this province. They will look at very similar aspects of the environment. Energy projects in Saskatchewan have typically been considered on the Environmental Assessment Act. Again, unless they've been very small, using already existing technology that's previously been approved. The assessment, a provincial assessment, may be undertaken jointly with the federal government, and at times the proponents, those who are making the applications, like that, because then at least you're moving forward at the same time. And then Saskatchewan will have permitting and other processes will follow as well, but we'll have this as well. Saskatchewan has, it's already been determined that we'll have a provincial environmental assessment as well. You've probably seen this before. It's the only SaskPower slide I have, just because it pulls all the timeline things together, right? So SaskPower has been doing feasibility study. They decided to proceed with planning. They've looked at technology. They've picked the BWRX. They're in the process of doing site evaluation. It's been announced. Estevan's one of 2 sites that's being considered. On the impact assessment side, they've been doing and are going to be doing a lot more pre-planning. That's been my world. Yeah, it takes time to plan, to pre-plan, then you got to plan, then you have to submit, then it has to be reviewed. It will go out for public review and consultation, many opportunities along the way. Somewhere along that line, as they build confidence in the approval process, they'll look to start to apply the licensing process, which is separate from the assessment process. That will go ahead. That's on the construction side. Then they'll also do that on the operating side. That will go ahead. And at some time in the future, all sorts of decisions are going to be made. Do we still want to go ahead and build it? Is it cost effective? Is it cost competitive? Again, do we still have confidence in the technology? All those things. There will be regulatory decisions along the way. Assuming that all happens at some point in the future, right now, 2029, 2030, then people will actually start work. And it's projected right now, 42 months construction. But again, we're all hoping that they'll learn from the Ontario Power experience with the first BWRX that's going to be built on the Darlington site. And now that Ontario Power said we're going to build 3 more on that site, they'll also gain that experience, which is, I think, just, again, I'm not an engineer, but from all the engineers I've ever worked with, learning from the experience of others is a valuable thing. So we can do that. Yeah.
So for the training to work at this site,
Yeah.
is that something someone will have to go to university for? Like, I was thinking I was supposed to 4-year training, or is that something that our college here could implement a program for?
There will be a mix of I would say 4-year engineers, 2-year technician type levels. And in this province, we already have experience. We already train environmental techs. We already train radiation techs. Predominantly happens in Northlands College for the uranium industry, but it's not a big add-on from my memory of the radiation protection 2-year program to, because radiation is radiation is radiation at the end of the day. It's just different, the different steps at a power plant versus mine, So there will be a mix of each. And just like today with Sask Power, some of those jobs are going to be, quote, in Sask Power's head office or in their engineering degree unit, and some are going to be at site. But all the other, again, balance of plant things, the electricians, that's all, and electricians. There's no nuclear electrician. They're going to be electricians at the end of the day. Like I said, uranium mining and milling, we have heavy equipment operators. We're not the only one with heavy equipment operators. We give them some special training on safety at our site, but that's all industry gives special training on safety at their site. Like,
curious, so you talk about the Ontario plant.
Yeah.
When, or again, where is that in the process? Kind of when's that being built?
They're actually already at site preparation. But they're still, like, the license design is still going through. Because they already operate both the Darlington and the Pickering nuclear power plants, they're already a licensed operator. They just have to show that they're going to be capable of operating this new type of reactor. And it is new because they're running all the CANDU reactors, which are they don't use enriched fuel, so they're going to have to show they've got the competence to handle the enriched fuel. But yeah, so they're sort of in this multiple stage going on here, but they've already looked, I understand, at site prep, and I think at one they've already started some site prep. The New Brunswick people are, again, just recently, I think just within the last month or so, have submitted, their impact assessment, so they're into this part of the process. They're also looking at a brand new reactor design, so that's going to go through some other things here too. So, and then along the way, of course, Sask Power, like everyone in industry now, is always out talking to people. So, and they can be, people in the community, Indigenous communities, and the like. Yeah.
You mentioned the federal regulatory system.
Yeah.
It goes 7 to 9 years, right? Is this like parallel, or when one is finished, does the next one start, or like with Sask Power potential? Or
no, it will some degree. It will move like this. So this is the greens, the impact assessment process. As they get confident in that, they're going to be preparing, submitting the construction license information. And again, after that, gain some experience, and they'll also start looking at submitting the operating license, because so they can move in parallel to some degree. But they're always pretty much built on, with confidence, we can take another step.
Ellen?
Is so for the actual GE SMR, has GE started fabrication on the actual SMR, or that's just still on paper right now?
No, they have their licensing of the technology application in both to the Canadian and the US Nuclear Regulatory Commission. And those two regulatory commissions have agreed to share knowledge and questions and information as to the technological review.
Like in terms of the actual equipment, has equipment actually been built yet? Is kind of my question.
I would say from everything I've read, no, they've not built one of these 300 megawatt reactors, but what they say is that they've been building boiling water reactors for 50, 60 years. They're on their 10th generation. They have designed and built a very large version of this reactor. And what they've done is they say they've made it from very large, like if I remember correctly, about 600 megawatts, but it's a very large reactor, down to 300. They've simplified it. They've taken out many elements that they think will allow it to work better, because I think simple, they're wanting that to be better. and they're taking advantage of fuel that already exists, fuel design, fuel enrichment levels, fuel enrichment, like all those things. They're taking advantage of 50, 60 years of their engineering of boiling water reactors in this. So,
Point of my question
Yeah.
is more in terms of the supply chain of the manufacturing of it. It hasn't been manufactured.
right, not fully, no. But again, the fuel side compared to, I'll say, to practically every other type of small modular reactor is very traditional fuel. All the other reactors are proposing largely new fuel types, which don't commercially exist yet. So if you may have heard of something called triso fuel, doesn't commercially exist yet. Haleo fuel doesn't commercially exist yet. This fuel commercially exists. Yeah.
On that note, then, does the 1,000 megawatt that Westinghouse is proposing, is that existing fuel or new fuel?
The new the Westinghouse, I think it's the AP 1000.
Yes.
It's also predominantly existing. So remember I said at the start, there's been generation 1, 2, 3, and most of the SMRs are going to be called generation 4. The BWRX and the new Westinghouse are probably called generation 3 plus. They're taking some of those new concepts, building them in, but they're also relying on existing concepts to bring them to market sooner.
So is the difference between a 3 plus and a 4 the fuel type?
I'd say it's a mix of both fuel type and design. Again, they have these new fuel types called triso or haleo, HAL, high assay low enriched uranium. So however you say HALEU together in one word. But they also largely don't rely on water as what's called the moderator, or water for the steam generation step. They don't rely on that. So they're proposing to use different things. They're proposing to use molten salts, proposing to use liquid metals, helium gas, all of which they believe provide an even extra layer of safety in the design. So it is a mix of both new fuel and new design, using less water than all, I'd say, the generation 3 and 3 pluses are.
Ruth.
Yes.
I have a question. There, you said it's the 4th generation.
A lot of the new ones are, yeah.
So there is some experience when a nuclear power plant has been installed somewhere in an environment in Canada. How did this presence of this plant affect the quality of life of the people that live nearby there? Are there any studies made? So I'm wondering, because of estimate situation that kind of has a problem with maybe future economic possibilities. This power plant that the nuclear that's supposed to come here, if it's not very big, so it does not bring many workplaces here. So I'm kind of wondering, would that be a motivation if that power plant will come? Will people be motivated to leave Estevan because of the power plant?
Al, can I?
Yeah.
So with my position here, what I'm doing, just yesterday, I had 2 conversations with 2 different groups that just tire kicking right now.
Yeah.
But they heard about the SMR and they want to put both of them. One's American, one's actually from Saskatchewan.
Yeah.
Are talking about putting a data farm here.
Uh-huh.
A server farm here, because they want to have a server farm or a big cluster of server computers nearer to the power source. They couldn't do that before because of the way of the politics and the commercial consumer demand. With coal, they can't do that. And we have some other things that are coming into the community that can't, because of ESGs and consumer grade stuff, can't come here until we do something like this. So there are people talking to us and economic and stuff like that. Beyond that, Al?
Sure. Yeah, so I'll try and answer that question maybe in 2 ways. So I would say largely all of Canada's first reactors, and we had an experimental reactor and they've all had really interesting numbers like NRX1 and National something research, they've largely all been built in a community called Chalk River, Ontario, outside of Ottawa. Been to Chalk River, been to the site. So several of them built there, and at present there is a proposal to build a demonstration site of another small modular reactor type called, the consortium's called Global First Power. It's going to be a micro modular reactor. It's proposed to also go at Chalk River, because Chalk River we were the second country in the world to support fission reaction. So we've been doing it for a long, long time. Then, of course, reactors have been built in Bruce County, in Clarion County, Southern Ontario for Darlington and Pickering, and outside the Gentil reactor in Quebec City was built outside Trois-Rivières. New Brunswick Power, Point-Le-Pro is not that far from Fredericton. So yeah, the large reactors tend to get built close to large population centers or large load centers. There have been many, 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 many studies on the potential health effects of having those reactors in those communities. There are also economic studies of the ones in Ontario for sure that I'm aware of. And this will leap ahead a little bit, but again, we take safety very seriously. We take radiation safety very, very seriously. So the reactors are designed to really minimize the amount of radiation that may ever get out of them and into the community. And there's monitoring all over all the communities around Darlington, around Pickering, around those things. And they get less than 1% of the it's called the millisievert public dose limit. It's a tiny it's less than you get from an X-ray. So living nearby a reactor that exists today, very, 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 very low potential exposure to radiation. And we've been monitoring this for a very long time, and health studies and.
Cool. I asked from South Power.
Yeah.
Whether they still do still in practice that to people who live nearby a nuclear power plant, every single person got iodine tablets at home to take. Just like say
Okay, so she was asking about iodine pills. So around large nuclear power plants, based on some unfortunate experience, including something called Chernobyl, but we knew about it before. We know that in the unlikely event of a very large reactor accident, one of the radioactive elements that could be released to the environment is radioactive iodine. Radioactive iodine can pretty quickly get into your thyroid, particularly if you're young. So as a precautionary measure, yeah, within, I can't remember the distance, but it's well marked out around all the large nuclear power plants. Yeah, there are, in the unlikely event of an emergency, and again, we use some of the language from the aircraft industry, aviation industry, in the unlikely event of emergency, you know what to do, and that includes taking an iodine pill. Because the wonderful thing about the thyroid is the first iodine it's seen, it takes up. So if the first iodine it sees is the pill you give it, it fills itself up, and if there's some radioactive iodine, it can enter your thyroid. So yes, it is true. Now, these small reactor designs, these Generation 4 designs, are designed to not have that type of accident. So what's called the footprint of the plant is actually significantly smaller. You have a very large zone around a large power plant to keep people away, again, in the unlikely event of an accident. You're trying to minimize the, it reaching people. You don't have that, you don't have need for that large of a footprint around these advanced small modular reactors because you don't have that chance of that type of an accident.
Why?
Part of it is, it's called the loss of coolant accident. They're designed not to lose coolant, and I can explain that a little bit. Right now, for most nuclear power plants, the cooling water, the circulating water, is done through pumps that require electronics and energy, right? There has to be power, there has to be electronic systems managing that. these new reactor designs don't require pumps or electric components for that cooling water circulation. They basically rely on gravity. The water goes in, it gets hot, it rises up as steam, it goes through a cooling system, gets back into water, and it goes back down. It's just a gravity that no one has to intervene. And no piece of equipment has to intervene. The older reactor types, there has to be an operator controlling the response. Now the response happens very incredibly fast, but they're designed, these new reactor types, to not require any operator intervention for that safety system to kick in because it's natural. We all know steam rises, as it cools, it comes back down as water, and it's just this natural circulation system.
I'm going to be a little annoying because I've seen your presentation.
Yeah.
And I know we're jumping around.
We are a bit, but
So
yeah, I'll take that into account.
No, not you.
Yeah.
How about we'll go a little bit and then we'll stop and ask some questions.
All right.
Okay, thanks.
So again, I won't talk about SaskPower more because we're into these issues and concerns, which could be, as we're talking about, radiation, safety, security, right? Waste management, all excellent questions. So if you're open to it, I'll try and give a very little short lesson on radiation. And maybe I'll rely on you, John, and your physics memory. But so people are often surprised that radiation is not only from nuclear power. It's around us all the time because it comes from or radiates from, fundamentally it's energy of some sort, comes from a source, travels through material or through space. We all get exposed to cosmic radiation every time we go outside. It's what gives us suntans and hopefully not sunburns. Sources of radiation, there are light, heat, sound. Generally speaking, many natural sources of radiation, including the sun, as I just said, various elements in the earth. It's in the soil, it's in the wall, it's in the food we eat. We're actually surrounded by radiation. We live in a radioactive world. Life evolved on this earth in actually a more radioactive environment than we have today through something called half-lives. And then in addition to what's called natural background, we also, all of us, have received radiation from technologies we use. Everyone had an X-ray. An X-ray is a source of radiation. Other tests, if you've been diagnosed or treated for cancer. My uncle, I won't say his name, but he got treated for prostate cancer by a small radioactive pellet was placed beside his prostate, and that's what killed the cancer. Okay. Actually, I have a, can I tell hopefully a funny story? Hopefully it's funny. I never know because it's got sex. Cameco, when I was at Cameco, we have a good friend of mine, radiation health physicist, okay? So, and we would get calls from time to time from people in the province saying, I think, is this radioactive? Should I be concerned? And often it happened for the example, the big pipe plant in Regina, which recycles pipe from the oil and gas industry because there's some radioactivity in fossil fuels. And sometimes there'd be enough there, it would trigger their alarm and they wouldn't initially be sure what to do. And so we would help out. But the funniest one we got one day was someone going through one of the scanners at the airport in Saskatoon. There are radiation scanners at all airports. So we take the stuff seriously. And triggered the radiation alarm, which doesn't happen often. And the fellow was confused because he's pulled out because radiation alarms, again, don't happen often. Where's the radioactive substance? And he goes, I have no idea. Like, I don't know. Well, apparently what happened, his wife had a nuclear medical treatment. Husband and wife experienced, relationship with each other. He picked up a dose of radiation and he went to get on a plane and he triggered the alarm. Shall we say it was a very interesting search. So, and radiation is even released from coal. Okay, there's something called naturally occurring radiation around us, and it's in all fossil fuels as well. It's in coal. So, all sorts of things, and we manage naturally occurring radioactive materials differently because the radiation level is so low. And again, it's part of background. What we particularly manage is any of the human man-made radiation sources. So, and how we manage it depends somewhat on the type of radiation there is. And there's fundamentally 3 types: alpha, beta, and gamma. I've included neutron here because some people do it and it's tied to nuclear power. So alpha radiation, it's called the heaviest, it's naturally occurring, it comes out of the decay of uranium. It's found often in radon in homes. It's just part of the natural decay series. Radon is a radioactive gas. It emits alpha particles. They're very heavy, relatively speaking, for atoms. They don't travel very far. Beta radiation is fundamentally cosmic radiation. It's all around us. It's there. Comes from the sun, comes from the universe. It also comes from carbon-14. Has everyone heard of carbon-14? Radioactive dating. It's how we know how old some organic materials are by how much carbon-14. Again, it's an isotope. Most carbon is carbon-12. A very small amount is carbon-14. And the ratio of carbon-12 to carbon-14 tells you how old the thing is. It's a little bit like the difference between uranium-238, uranium-235. They're isotopes. Then we also have gamma, which is like an X-ray. It's electromagnetic. That's really made by, well, the nuclear medical tests we get and those kind of things, largely. And then there's neutrons, which come, again, from the splitting of the atom. It's the key, it's fission, it's key to nuclear power. A neutron on its own is not radioactive, but basically everything it runs into is radioactive. So it's included largely in this list. And again, it's important to know the type of radioactivity because we can manage it differently. They all have different energy levels and different abilities to pass through or to penetrate materials. These alpha particles, again, very large, very heavy, very slow moving by comparison. Well, they can be blocked by a single sheet of paper or your skin. They won't penetrate, but you don't want to breathe them in because your lungs have no protective layer called skin. So you don't want to so that's why if anybody ever heard of someone with radon gas in their home over a certain level, then you come in and you put in pumps or air replacement system like to remove the radon from the home. And because it's heavy, it's a gas, it tends to sink down the basement. So if you've heard of people with radon issues, it's in basements. This beta particle, again, the thing comes from the sun. It can be blocked by sheets of plywood. It can be blocked by clothing. Again, it's faster, so they can penetrate a little further, again, than a sheet of paper, but they're less likely to cause harm because they have less energy overall. Gamma and neutrons require thicker material. So in this case, they show like a meter of concrete as a shielding. Gamma rays, X-rays can pass entirely through your body. The other ones typically cannot. And as they pass through, they may cause some damage to tissue. That's why they can be used to treat cancers, because they can cause damage to tissue. They can kill cancers. Again, neutrons, not direct source, but we still want to control where they go. So there's all sorts of shielding around nuclear power plants because you don't want the neutrons running into other things and potentially splitting them apart and again, becoming a source of radiation. So again, so even though there's radiation all around us, the real issue is exposure. How much are we exposed to? Again, we all live in natural background. Natural background in Canada is about what's called 3 millisieverts. And a millisievert is just a measure of radioactivity that can interact with the body. The typical annual exposure to a nuclear worker in Canada is 1 millisievert, so less than background. We do lots of things to protect workers from radiation in the industry. Cameco, underground, for example, because radon can come out of uranium decay series, I can't say it anymore, I'm not with Cameco anymore. When I was there, Cameco was pumping 1 million cubic meters of air a minute into the mines to flush the radon out, to always ensure there's fresh air, always ensure there's fresh air. You're underground at the mine in Cameco and you feel wind at your back. and that's always pushing it away. So we design radiation protection into all parts of the nuclear industry. So workers get exposed to a level of radiation across Canada on average that's about the same amount that the Canadian Nuclear Safety Commission says the public should not be exposed to anything more than 1 millisievert. And where I said again, the people around the Ontario plants, they get less than 1% of 1 millisievert. All the people who live in those communities. That's a very, very small. But again, we design to do that in the industry. So again, the people who live around Darlington, Pickering get about the same exposure you get from a chest X-ray. The Canadian Light Source in Saskatoon, which again is a nuclear facility, they get even less exposure just because that's the type of facility it is, the type of radiation it creates, those kind of things. And workers in Canada have an annual limit of no more than 50 millisieverts, but I can tell you as an industry, we would never allow anyone to get to that. We have what's called action levels, which tend to be 10% of that level or even less. So if anyone gets 5 millisievert for some reason, we act. If anyone's trending towards an action level, you act. Like, you don't wait for exposure to happen, you manage it and you try and minimize it. Yes?
How do you know how much exposure you have?
In the industry, workers all carry little pieces of sensors on them that measure that. And they'll measure the alpha, beta, gamma. Some of it has to be calculated. So you track where people go in a plant, you track how much time they spend in a plant, and it's reported up to an independent agency. It's recorded for life. So even if you move from one company to another, there is a central repository of your dose exposure in Canada.
What happens to that worker when they get to say 50, their annual limit's up in June, just happens?
Hey.
Is that like a WCB thing or? I'm just curious.
I'm honestly, I'm not aware of anyone
Ever?
honestly
Okay.
getting near 50. So, and actually, it's marked this way, it's the annual limit, but what we managed to is, no, you're trying to even not do 50 over 5 years. Again, we build protection in. You don't want to ever run up to a regulatory limit. That's tends to not be a good thing. So you always try and keep below.
I thought that there was the 5-year limit was 100 millisieverts. Thought was what the 5-year limit was. But
Yeah,
that's
so
my recollection is.
no, it's a fair recollection. Yeah, you may be right. It's also more, again, how industry manages itself. Like yeah, you're right. It might be 100 over 5 years. So, well, that means 20 millisieverts a year, right? That's what you're trying to. So, yeah, we take care of this kind of thing.
Al?
Yeah.
We've got 2 online fans here.
Oh, okay.
And they have 2 questions for you.
Sure.
One is, could an SMR use salt water as coolant? Or is that about, could they do salt water as a coolant?
I don't know. Certainly, the existing reactor fleet that needs cooling water does use water from lakes, from rivers, and from the ocean. But like a coal plant, any water that actually enters the system has to be incredibly high purity water. But cooling water, which never is not supposed to interact with any nuclear component. But I honestly don't know yet on the SMR front.
And then we have another one on the condensation of steam through the turbine.
Yeah.
Will we need to be utilizing a cooling tower to dissipate the water heat, or will there be attempting to recover this energy with heat pump technologies?
In my extra slides, I have a slide of that, so I'll try and answer it. So most power plants use water cooling systems. They have the option of air-cooled systems. Actually, very, very few use air. It is a possibility to use air, but again, some of these Generation 4 reactors, small modular reactor types, which are proposing to use helium gas or molten salts, those things, aren't water requirement at all. And one of the interesting things about that from an industry perspective is, so if you're not running that excess heat through a cooling pond, are there some industrial uses you can make of that heat, right? There's already using Shan for greenhouse, but could you use that heat for other industrial processes? Because if the SMRs because they have very small footprints by comparison, can be located close to industry, maybe we can use that heat and replace the amount of natural gas we burn to dry some product, or preheat things, you know, in the cement industry before, because to make cement, you may know needs really high temperature heat. So, yeah, and people are looking at, quote, what they call hybrid technology. So perhaps heat pumps and the like, yeah, could be deployed here, but there also is interest in using the heat, not just trying to find some way to dissipate it, but actually use it for other processes. This is another look at radiation dose. You may not be able to read it here, but this is the very bottom. Typical dose from living 1 year within a few kilometers of an operating nuclear plant in Canada, 0.001 millisievert. Dental X-ray is more than that, 0.005 millisievert. Chest X-ray, already said, 0.1 millisievert. You take a flight across Canada, you'll get a radiation dose. As the higher up you go, the more solar radiation you get. The average background dose in Canada, again, about 3 millisieverts. You go to Vancouver on the water level, ocean, sea level, it's less than 1% because you're lower to the ground. You go to somewhere high altitude and you get more. That's shown here. Annual public dose, again, 1 millisievert, same to what workers average to get, lower than background. Chest X-ray or a CT scan, 7 millisievert. So that's why, you know, you can use nuclear medicine, but we should also be careful with how often, you know, like any, you know, use medical purposes for benefit, so you don't, you know, don't run out and try and get a CT scan every week. Like I would say, not probably a smart thing to do. And the annual dose limit, you may have heard the astronauts are working up in the space station because you're really fully exposed to cosmic radiation, 150 millisievert. Yeah, 5-year dose limit, 100 millisievert in Canada. And radiation sickness, people say, you know, if I'm exposed, am I going to get sick? Doses that may cause symptoms of radiation systems is 1,000 millisievert. That's a very, you know, high number for a reason, you know? So we do our best to keep exposures way down here, and we do everything we can to avoid like anything, ever getting a 1,000 millisievert dose. And I've had people say, again, in Canada, you know, how do you really know this 1 millisievert or his background is safe, right? Well, there are parts of the world where the average background dose is Niger, 95 millisieverts. You know, the list here we got, in Northern Iran, 260 millisieverts. If you've ever been to the White Cliff of Dover, it's it's up there too. Yeah, so it varies around the world. There are hundreds of millions of people living in areas that have radiation doses high, what we would consider high. So to protect ourselves from radiation, there's 3 fundamental things you'll hear people talk about. You try and, it's called time, distance, and shielding. We're going to seek to minimize the amount of time wherever we're exposed to a radiation source. We're going to keep our distance from it. And if we can't do those things, we're going to shield it. Anyone in oil and gas? Anyone use a radioactive source in oil and gas? How many do you use? Many. Yeah. So you can talk about it there. Pretty much all radioactive sources, my memory in oil and gas is they're all shielded. They're all kept away from people. They're under storage. And you minimize, you only take them out when you need them. You don't leave them out and about. You don't do that. Has everyone had an X-ray? Just think about that, you know, that experience of an X-ray. You know, again, we always try and minimize the amount of time an X-ray technician might get exposed, right? They put you in the room to take the X-ray, they step out. If they can't step out, they step away. They can't, and if they step away, they can't get out, they're behind some type of shielding. The parts of your body we don't want irradiated tend to get a lead apron put on them. So these principles of radiation safety occur throughout the industry that uses nuclear. And that's not just power. You'll see this in everything nuclear. We use it in the mines, mills, all those steps. These elements of radiation safety are used. For nuclear power plants, back on the question about when it's used fuel, is it hot? Yeah, so that's all done autonomously. People don't go near it. Time, distance, shielding. It's stored in shield containers. It's stored at these pools. Sorry, I'm not an engineer, but sometimes really, you look at a spent nuclear reactor fuel or used fuel reactor cooling pool, which I've done, you think, wow, I could reach down and touch it, but you can't because it's like 40 meters deep, but the water is so clean, it just looks like it's right there, but it's not. It's like way down deep. Like water is actually a great shield for radiation. Is that okay? That make sense? And again, for these new reactor designs, for these SMRs, these generation 3+ or even 4, again, I said earlier, they're all designed to eliminate that chance of a loss of coolant control. They all have these, again, passive cooling features, so you don't need someone to intervene. Again, we don't have safety-related electric pumps because electric pumps can fail. It's not a place you want that to happen, ideally, or operator intervention. Again, BWRX is one of those ones that uses natural circulation. Steam goes up basically into a swimming pool above it. It cools it. It goes back down as water and gets turned back into steam. And they're also doing things like constructing them underground. If they're underground, they're less vulnerable to extreme weather incidents. They're less vulnerable to earthquakes. And you can do that with the smaller reactors. And the ground, the soil, is also a wonderful shield. So those are some of the features you'll see in the SMR designs that are coming forward here. We also take into account as much as we can where particularly new nuclear reactors are put, because you have that choice. Like a uranium mine, the mine is where the uranium is. Like you can't move it. But reactors, we have some choices. And there's, right now, I'd say for the SMR world, there are these 3 challenges: the demonstration projects, the utility scale SMRs, industry scale micromodular reactors. These are new technologies, so we have to find good places to try them, and we have to help them happen well. So again, in Canada, an MMR demonstration project happening at Chalk River, which has been the home to many experimental reactors over the years in Canada. So selected there for a reason. The first utility scale Ontario Power existing site with an experienced operator, right? We're trying to pick good siting places to try and address some of these siting challenges. All these first of a kind, we really need to happen really well. They have to be well managed, well executed, well constructed. Because again, unfortunately, part of the criticism of nuclear power, the large nuclear power plants, is they take a long time, they have cost overruns, they're more expensive. So we need SMRs to really do well on that front. And so that's why we're looking to do demonstration at or on existing nuclear sites. This global first power at Chalk River is one of these high temperature gas cooled units. So again, it will not need water for cooling. It's going to rely on helium gas for cooling. And again, all the first utilities are being looked to build on existing sites like Ontario Power. Now, hopefully, this will help us all address some of the licensing challenge. Sask Power, if we go ahead, we're going to be among the first full utility scale SMR deployments at a site not already used before. So that can be really exciting, or can raise questions, because new generally triggers all sorts of issues in a review process, right? New technology, new site. There are some new licensing requirements possibly for these SMRs that are being consideration. Again, Ontario's trying to combine an approved technology, once the technology gets approved, with an approved site, with an approved operator to help move it forward. And anything that's new raises questions, like policy questions. So I already mentioned Warman refinery proposed for Warman. It would have been a great addition to the nuclear fuel cycle in the province. It got turned down in environmental assessment. They picked a terrible site. At the time it was proposed, the lot of fear about nuclear was it's tied to the weapons cycle. And they proposed it in the middle of a Mennonite community, pacifist community that doesn't like war. Bad siting choice. One of the challenges they had there. Yeah, the first of the, and I can speak to waste, but there's the used fuel waste, and then there's low and intermediate fuel waste. So the very first time Canada tried to find a place to put all the low-level waste, that can come out of dental offices and medical offices, all those kinds of things. Again, picked a terrible site. Just made a bad site choice. And the current high-level repository work is trying to address that by not picking a site, by inviting people to be a host. We finally learned and went, let's not just say, here, but who wants it? And how do we help you make the choice if you want it? So we are starting to learn in the industry. And I think SaskPower largely is also looking for people who want to host a site. Now in the choice of picking nuclear, people will say, again, particularly those who are opposed to it, well, we should just build solar and wind, right? Solar and wind is better, right? Just is. Well, I'm a big believer in something called life cycle assessment. I'm a big believer in looking not only what it looks like when it's running, I want to see where it all comes from and what's going to happen to it when it's done. So these are, I'll go through, if you're okay with it, several of these life cycle things. So materials, how much do you need to build, operate something, right? Solar, photovoltaic solar needs more than 16,000 tons of materials to generate a terawatt hour of electricity. That's a lot of electricity, but this was to allow it to all be equalized. So you need a lot of material for solar. Wind, more than 10,000 tons of material for a terawatt hour. As a mining person, we actually like it. There's much more materials required for green stuff than there is for fossil. So if you're into mining, this is good. Hydro, more than 14,000 tons of material, largely in cement. Hydro dams are big concrete structures, so you need lots of cement. Geothermal significantly falls off, and I know geothermal is being considered there as well. Say, a little more than 5,000 tons for a terawatt hour. Nuclear, way down here. And this is life from mining, milling, refining, conversion, enrichment, fuel fabrication, fuel operation, storage, decommissioning, disposal, all in. So if we're worried about how much material we use in this world, nuclear for electricity generation needs the least amount of material. How available is the energy? Well, there's life cycle considerations of capacity factors. Nuclear is the most reliable. We all like being able to turn the powers on, lights on, run our computers, run our offices, run our shops, heat our plants, heat our homes. We like that. These are the capacity factors across the entire United States for all generation types. Nuclear, more than 90%. Geothermal, good base load, more than 70% available. Natural gas, more than 50. Coal, more than 40. Hydro, more than 30. Wind, little less than that. Solar, less than 25%. So the interesting part from a land perspective, and this is, I think, some of the reason why there's pushback in Alberta over solar and wind installations, is the land requirement. To get as much power for a nuclear power plant from solar, you have to build 4 times the capacity. You want a 300 megawatt nuclear power plant, you have to build at least 1,200 megawatt solar. You have to build about 900 megawatt or more wind. So, people that sometimes are opponents of nuclear, But from reliability, if we all like having power and all the things we use with power, I'm a big fan of nuclear. All right, I know I'm in coal country, but greenhouse gas emissions also be talked about. So there's a really great group in the US, one of their several national labs, a national lab on renewable energy, has looked at all types of energy options for greenhouse gas emissions. You know, and I've got friends who love biopower. Can we burn, you know, flax straw, all those kind of things? Well, it can have low emissions, but it's got this huge range of greenhouse gas emissions depending on what you're burning. There's not a lot of energy in flax straw by comparison, right? Particularly again to now, so life cycle basis, so to build solar plants, to build concentrated solar plants, to build geothermal, you still have to have materials. And to build those materials, you create greenhouse gas emissions. So they're all pretty low, right? All these renewables are pretty low. I'll pop over batteries because they're not actually sources of electricity. They just are ways to help us manage electricity. And you look at nuclear. The big bar is sort of the ranges that exist in studies, and the colorful bars are the ones that have been really diligently reviewed. So the colored bars are the better studies. But you see, nuclear energy, wind, ocean, hydropower, geothermal, they're all pretty much the same from a carbon perspective. So if you are worried about climate change and global warming, nuclear, you know, can be part of the answer there. Water, the question came up about water, right? Most, again, power plants, natural gas, coal, that use water to generate steam, all need some way to cool it, so we all need access to water. It's our largest source of water use today for the reactor designs that, again, use steam. They take a lot of water out of the system, but they don't consume very much. Consumption is less than 2% of all the water. So, you know, we've got Boundary Dam, the lake there, we got, right, that's a cooling facility, but there's always, right, there's still always water in Boundary. From when I went fishing there was water in Boundary. So we use a lot of it, but we don't consume very much. Now, are there environmental concerns with that? Yes, like with any time, because we are heating the water, so it may alter local aquatic ecosystems. They try and find places to put it to minimize the likelihood that happens. So that's why the very large reactors are on very large bodies of water. Again, the new reactor designs that don't need that much water, you know, again, more location choices. But interesting, we're also finding in the last 10 years or so that climate change is impacting the ability of any power plant that needs water for cooling, because we're getting increasing temperatures, so the body of water is itself getting warmer, so it's not as good at cooling. We're getting drought in some situations, we're getting flooding in others, so you know, this has to be taken into account. And they take into account, again, where we look to put reactors, the technology we use, can we recycle the water, all those kind of things. And as I said already, there are several new designs that are proposing not to use water. Safety, left-hand side of this, a group has done a calculation of death rate from accidents and air pollution. It's my other connection to the aircraft industry, right? Hundreds and hundreds and hundreds of aircraft fly safely every day. That doesn't make the news. If a plane crashes, it makes the news. Nuclear is similar. We got hundreds of nuclear power plants operating safely every day. That's not in the news, but if there's an accident, fortunately, there have been a very small number of nuclear accidents. So this looks at the death rate. Unfortunately, coal, largely influenced, I can tell you, by coal mining practices in China, which are not, shall we say, as strong. So we have, if you count death as the ultimate safety impact, nuclear taking all in, including deaths from Chernobyl and Fukushima, right, 0.03 deaths, pretty much like solar and wind. No. So it is among the safest and the cleanest sources of energy, all in. And we already had some questions about waste. Again, we have options for dealing with it. If we're not going to recycle, we can do deep geological disposal. I know one of my engineering friends said the CANDU reactor fuel after about 100 years is no more radioactive than what we mine here in Saskatchewan. You could readily reuse it from a radioactivity perspective. And again, a plus, all nuclear waste is solid, it's contained. 80% of all radioactive waste of all types, what are called low intermediate, because again, medical offices generate nuclear waste, and it's 80% of all that's ever been generated is now in disposal. Around 95% of all radioactive waste is what's called low or intermediate. Very, very small portions of nuclear waste are what's called high-level waste, so it's fuel waste. It's less than 1% of all the radioactive waste that's ever been generated. Very small amount. And these are just some other numbers over. There has again been reprocessing, reuse of fuel in several countries. Most countries, I said most, but we have ways to finance this. We're not asking people to, the industry finds the money to ensure this all happens. And of all hazardous waste shipped every year, and there's lots of hazardous waste shipped around the world, less than 5% is radioactive. And of that, less than 10% is related to nuclear power. We safely manage waste. I also get the question, because I thank the question about recycle, because everyone says, well, but yeah, we don't have a way to deal with the waste. Well, I will challenge you, and I just couldn't find the resource, and I know I have have you ever thought about how you recycle a wind turbine? You probably have already heard up until about now, everything Apple's ever made is not recyclable. You've heard about the problem with e-waste? Everyone points to nuclear saying you have a waste issue. Well, if we have a waste issue, which it's solid and contained and we know where it is and we have money to pay for it, but yet Apple has no way to deal with its e-waste or I'm happy to have a waste debate. Very happy to have a waste debate, And I know I even had some friends say, well, but it could be. Well, but then so could nuclear. If you want me to accept that everything green could be recycled, you have to give me that so could nuclear, because I already have a history of recycling spent nuclear fuel. I already have that history. You don't. I have in my area, people say, oh, we don't need new lithium mines. We can just recycle your lithium. No, there's no lithium recycling today. But we're all going to have lithium in our batteries. So I'm coming to an end here with what I have. So just, if you're interested in supporting the nuclear option in the province, I'm going to say there are some things I would encourage you to think you can do. It's a term called social license. It's a bit of an old term now. You may have heard not in my backyard, right? People don't like things that are new or different and all sorts. And again, there can be fear factors and concerns for impacts. I understand. But I think we can help people overcome and help build the conditions for social license. So you can educate yourself about nuclear. There was an offer of the site, the NWMO site. There's lots of material out there. And hopefully what you're learning tonight is, you found informative. And then engage others. My experience is don't be afraid to engage others in the question. And if you don't know, you just say, I don't know. But I'm prepared to learn. And I would encourage you to learn. Like you say that to others, like, please learn. Encourage energy literacy. So I'm going to tell a story. I went to school for a little while in Ontario, around the time Ontario Power was trying to figure out where they're going to get power from for the next 25 years. And they asked the people in Ontario where they get their hydro from. That's what people in Ontario call electricity. It's hydro. And they said, well, I get electricity from the plug in my wall. And you ask them, well, how do you get more electricity? I put more plugs in my wall. That was the opinion of 88% of the Ontario population. I don't know how you do energy planning if people think I get more energy by putting more plugs in my wall. So we have to help people understand, I think, that every energy option has pros and cons. Again, right? If you're worried about how much materials have to be mined, well, then look at how much material is needed for solar and wind. Already today, there's more materials being mined for energy than there ever has been because of we're going solar and wind. there's hundreds of more kilograms of metals in a battery electric vehicle than one powered by gas. Hundreds. So as miners, we like this because it's just more materials and more mine stuff. Like it's just, so I think we have to help people understand, yeah, that there's pros and cons, and it can be on materials or land used, or again, the concern seems to be the concern in Alberta, water consumption, safety. Okay. I like to say we should promote common language or consistent language on the value of nuclear and what it can do to help us, particularly in greenhouse gas emissions reduction. And again, I looked to Alberta, got colleagues there in the oil sands industry. What's the other name for the oil sands industry? The tar sands. That can happen. You can get, people can use language against your energy option. Right? No one talks about coal and the energy it provides. They just talk about how dirty coal is, right? Language matters in the energy debate. And I do encourage people to fight fiction with facts, because there's lots of fiction out there. And we all know this through social media and other things, lots of it. So again, hopefully some of the stuff I provided here, you'll see everything, I'm gonna say, practically everything I provided here, I have the resource for. Like I can tell you where I got that from. And I do enjoy, if you've never heard of her before, there's a woman called Isabel Bonk. Sorry, I'm not great on social media. Sorry, I'm of the age where, I say, when I started school, there weren't computers of any type yet. My grade 12 grad gift was a typewriter, so I could, anyone even use a typewriter, right, anymore? So, she's a young woman, smart, nuclear influencer. Her site's called Isodope. She's really funny and engaging, all those things that we want young people to be when they're on social media, but really well grounded in knowledge. So with that, I want to say thank you. I have absolutely no idea of time, but I honestly, I've really enjoyed it. And I hope you had too. And I'm still happy to take questions if you want to keep discussing it, because I drove all this way from Saskatoon. I'm not going home, so I'm here tonight. So yeah, more questions. Yeah.
Just one thing you haven't talked about is meltdown risk. Like in terms of, I've had conversations with people that are fearful about meltdown, and like my understanding is that they've become so safe that we have very little risk of that. But even in the event of a meltdown, like what we saw at Fukushima, what kind of actual human impacts were there? Like, how bad was Fukushima even? Right? Like,
Sure.
I don't know that.
Yeah, a great question, and I do have a slide on it. I'm trying to decide if I should use it or not. So, yeah, that loss of coolant accident, which is what happened in Fukushima, is what's being designed out of all the new reactor designs, so that there is not core meltdown. 3 Mile Island, anyone heard of 3 Mile Island, which is an accident back in the 1970s? It was, quote, the worst nuclear accident in the United States history. It was a partial core meltdown, 0 deaths, 0, I'm going to say 0 harm, because it actually went to court many, many times in the US. The radiation that got out of the plant is 5% of an X-ray dose. And it significantly blocked construction of new nuclear plants at that time, because it happened to happen just a few months out after a movie came out called The China Syndrome, which projected that there could be a core meltdown and it would melt through the reactor down to the center of the earth all the way to China. That's how it got the name China Syndrome. So it was in the popular culture that could happen, and then it almost happened, and because there was an electric failure in one of the valves. So again, we're designing that stuff, we're designing that out. Like I said, we do learn. Fukushima, and I can cite ahead, but I'll go by memory, had 1 death from the accident.
But Fukushima still at the west coast, in the aquatic area, there is lots of life, animal life that is actually still dying.
Okay, so so this is going to be one of my, I'll try and bring some of the facts here. So again, so on the human side, there was 1 death. there were, I believe, I mean, I can't remember if it's more than 17,000, more than 19,000 deaths from the earthquake and the tidal wave. And that's not to minimize, right? But so there's one death from the nuclear accident itself. There was impact on aquatic life immediately afterwards, but the studies that show 10 years later largely recovered. If you look even at Chernobyl, the environmental area outside of the immediate area around Chernobyl has got better biodiversity and animal populations than before, because we took people out of the environment, and we also took dogs and cats out. Amazing how many animals dogs and cats will kill in a community. There's a uranium mine in Australia, which is in the middle of a national park, and the town that supports it, it's against the law to have a dog or a cat, because they kill more wildlife than anything that happens at the mine. So you actually can't have it if you live in Jabiluka. So yeah, I'm full of all these strange little things.
I got a question from someone online here.
Yeah.
What is the estimated labor force required to operate a standalone BWRX 300?
Right. I do have that. I'm just going to flip through. And here happen to be my ones on accidents. Right? Yeah. So again, 3 Mile Island, the worst one in the U.S., no injuries, death, or direct health effects caused by the accident, 3 Mile Island. I had talked to someone the other day who was surprised that when they flew into that community to go visit family, the other reactors are still running at 3 Mile Island. They were never shut down because they were never harmed by the accident. Still running. Chernobyl, again, the most serious accident, right? 30 direct deaths there, 2 workers, 28 firefighters. Studies done 20 years later, 19 more first responders had died 20 years after the fact. Those first responders were experienced significant doses. That is part of reactor design. That reactor didn't have any containment structure to contain the radioactivity in the event of an accident. It was also caused by the Soviets not telling anybody the accident happened, so nobody took their iodine tablets to protect them, like out in the community. Like the Soviets said, accident, one accident. For 48 hours, they went, not us, you know. Radioactive alarms were going off in Sweden and Finland, and they were thinking, what's going on at our plants? My God. Well, it wasn't coming from them, it was coming from Chernobyl. And again, unfortunately, about 4,000 cases of childhood thyroid cancer with 9 deaths, because the Soviets didn't tell anyone about it, so they couldn't take the preventive measures that they should have taken. And again, radiation levels all over there. Fukushima was the worst case for a Western designed reactor at that time. 0 direct deaths. The one person who did die was in one of those first responders. There were more than 2,000 deaths from evacuees who couldn't tolerate the stress of being forcibly relocated. Terrible thing. And again, we've had, but here are the workforce requirements. So yeah, I got these from SaskPower. They're pretty consistent with what's in, there's a public study of SMRs in Canada. So during that planning stage, they expect to have about 180 people working with respect to a plant, and those will be engineers. A lot of those will be mechanical engineers, civil engineers, standard engineering fare. Will there be some nuclear engineers? Yeah. Lots of technical support staff and environmental technicians. During construction, they're proposing about 1,760, and that's all pretty standard construction trades, because again, the nuclear things that are going to get manufactured in a manufacturing plant will come here already assembled. They'll come here as a, so that's all, will be all pretty standard stuff. And then in operation, you're going to have, they're projecting about 180 people, and there will be some nuclear operators who will need training, particularly that. Still lots of non-nuclear operators. There'll be chemistry technician people, make sure the water in the pool that's above the reactor is the right type of water chemistry, all those wonderful things. There'll be maintenance technicians, fuel techs, environmental technicians, there'll be radiation technicians. There'll be still lots of utility staff, just like there is at Shand or Boundary, security staff, and there'll still be engineering technical support. In operation, I would not know how many, again, ultimately might be based here or Regina or, if so, but those are the numbers I'm aware of, and they're pretty consistent with another study. And I did do a comparison against the US reactor experience with large reactors. And if you take a 1,000 megawatt reactor, divide by 3, yeah, you roughly get this. It's not as many as a large reactor because it's not a large reactor. It'd be my simple answer. So.
And I got another question online, but from what I also going through the SaskPower thing, I think that 180 is per SMR, and we're going to get 2.
Right, per SMR.
So we'll get 360.
Right.
Just
Sorry,
to be clear,
I said that. Yeah, this is per unit.
The other question is, do you expect issues from the U.S. with the possibility of building a nuclear facility 15 kilometers from the border?
Wow, that's an interesting question. Yeah, is it possible? Sure. My experience on proposing something, there are the people who are closest to something that's being proposed. There are people who may be the most impacted by it. With what's proposed, they could either lose a job or have a chance to gain a job. There will be those who are interested in it from a technical perspective or social perspective, right? The Warman refinery drew lots of interest from all over the place about nuclear weapons. Like, not just people, this was like everywhere. Could there be? Sure, and particularly if they're not aware of, if I remember the maps correctly, I don't believe, there's not a nuclear power plant in the Dakotas. I'm just trying to remember where all the dots are on the map, but so if you're not experienced with it, sure, that could attract attention because people just may not know. They may have that question, what if there's a core meltdown and the wind blows, into the Dakotas? Could they be concerned if they don't know? Sure.
And I think, what do you guys say? We wrap it up, but you'll stick around for just questions? Okay, cool. So before I say thank you, I just want to let people know. So this is just one of first events. So oil and gas people, coal, on October the 5th in Regina, as a part of the energy show that will be of the 4th, Al, SIMSA, and the Tech Hub, myself, will be hosting an event more about the supply chain stuff. We don't have all the answers yet. We're all collecting it. But if you're going to the energy show, or if you guys want to know more about how you can be part of the supply chain, that's happening. And as we're going to have more events here coming into Estevan.
Yeah, and for me, it's about the supply chain for mining. We think a lot of what happens in oil and gas could potentially cross over to mining. Some of the innovative things you do in oil and gas potentially could cross over to mining. That's really what I'm in. Most of my career, again, has been in mining, so that's my area of interest, but there will be talk on the nuclear supply chain side. But maybe there's opportunities in the mining supply chain side outside of coal or out of oil and gas people could cross into.
And then there's one thing I just want to end. Me and Greenpeace have one thing in common. We were both born in Vancouver. But something that I ran across that I think I hear a number of people worried about, are we going to have protesters if we have this? And I know I said we're not, but this I found really interesting. So the EU has put nuclear power on the official list of green energy for subsidies and what have you. Greenpeace is suing the EU to stop that. John's favorite person, Greta Thunberg, and her group are suing to be, what do they call it?
Interveners.
Interveners against Greenpeace. So there's this huge thing going on. So the same kind of discussions that we're having in our community, it's happening globally. So just something to think about. So want to thank you so much.
You're very welcome.
Really appreciate it. And we'll have some beers afterwards.
Yeah, but there's food and other things over here. And I'm happy to stay for a few minutes as long as my brother's not starving. He's probably been eating all along that's here. So
thank you.
Yeah, or else, again, so we can answer a few more up here, or we can just answer them one-on-one I hope you found it informative. I hope it helped. And yeah, I'm very happy to come down here because again, I've got the family ties to the area and family ties to